Hello everybody, here is your last section in chapter 8, 8-6, choosing a factoring method. Now here we're not learning any new methods. We've learned all the methods that we're going to learn. We're just going to put all the different methods together. Given a problem, we're going to teach you a step-by-step process to go through to determine which method you're going to use in order to factor the problem that you are given. Alright, so the objective, choose the method that you're going to use to factor a polynomial. And we're going to learn in the next slide to be able to tell whether something is fully factored or not. A polynomial is fully factored when it is written as a product that cannot be factored any further. So just as we reduce fractions, we keep reducing fractions or simplifying fractions until they cannot be simplified any further. That's the exact same thing that we do when we're factoring. We don't want to leave anything in our answer that can be factored further. So let's just look at these three and determine whether or not they are fully factored or not. In this first example, I see that this appears to be a greatest common factor. And then in parentheses here, they wrote what they were left with after they took out the greatest common factor. But I noticed something here. I noticed 6x minus 4. I see that both of those terms have a factor of 2 in them. So I know when this person factored out what they thought was the greatest common factor of 3x squared, that really was not the greatest common factor. There was a bigger number that could have been factored out. So if I take 6x minus 4, I know I can factor out a 2 from that. So if I factor out a 2, I'm left with 3x minus 2. Okay, so I'm going to take this extra 2 that I factored out and multiply it times the 3x squared, and that gives me 6x squared, which is what should have been their greatest common factor. Now when I look at this inside my parentheses here, this 3x minus 2, those are in the most simplified form that they can be in. There's no greatest common factor between 3 and 2, whereas there was a greatest common factor of 6 and 4. Let's look at the next example. X squared plus 1 times x minus 5. This, you might think it looks like perfect squares. X squared is a perfect square and 1 is a perfect square. But because of that plus sign right there, that is a sum of squares, and we know a sum of squares cannot be simplified. It cannot be factored. So x squared plus 1 cannot be factored anymore. X minus 5 is in its simplest terms. I can't do anything with that. So this is fully factored. The next example, 4x plus 4 and x plus 1. This x plus 1 looks really good. That's definitely in its simplest form. But the 4x plus 4, do you realize anything about that? Okay, you should realize that there's a factor of 4 in each of the 4x and the 4. So I can factor out the greatest common factor of 4, and I'm left with 4 on the outside and then x plus 1 on the inside, and this x plus 1. So I can rewrite this problem, or this answer, as 4 times x plus 1, that quantity squared. This answer that I'm circling is fully factored. The problem we were given is not fully factored because there's a greatest common factor in 4x and 4. Alright, so here are the steps. You need to take a minute and write these down. This is the process we're going to go through to factor a given polynomial. First thing we always want to check for is the greatest common factor. We want to look at a problem and see if there is a greatest common factor. If there is one, we factor it out at the very beginning. After we've taken care of our greatest common factor, we look to see if there's a special product, which we just learned about. Is there a difference of squares or a perfect square trinomial? If you recognize a difference of squares or a perfect square trinomial, you go ahead and factor that first after you've done the greatest common factor. If there's not a difference of squares or a perfect square trinomial, you go on to step 3, which is factoring x squared plus bx plus c or ax squared plus bx plus c. That's when the a is not a 1. So we've learned that a couple days ago. And then last, before you circle your answer and say you're finished, you want to make sure there are no other common factors. You want to make sure your answer is fully factored. So let's take a look at this example. I have 10x squared plus 48x plus 32. According to my steps that you wrote down, the first thing I want to check for is the greatest common factor. The greatest common factor between all of those terms is a 2. I can't factor out an x because the 32 doesn't have an x. So what am I left with after I do that? I'm left with this that I'm writing here in my parentheses. Alright, so now that I'm here, I want to look at this inside bit right here and see, can I factor that? Is it, I go back to my steps, is it a sum of squares, or a difference of two squares? I'm sorry, not sum of squares. Is it a difference of squares? Nope. Is it a perfect square trinomial? No. The 16 right here is a perfect square, but this 5x squared is not a perfect square. So it's not a perfect square trinomial. So I go on to my next step, step 3, which is factoring ax squared plus bx plus c. What do I do when this occurs? I do my t and my x to factor. So I'm going to multiply 5 times 16 to get, let's see here, 80. I have my 24 down here at the bottom. I think what multiplies to give me 80, that adds to give me 24. Let's see here, what's that going to be, guys? 20 times 4, perfect. Now I make my t. I have 5x, my 20 and 4. Then I'm going to simplify those a little bit. We should be really good at this process by now, guys. So I see what my two binomials are going to be. That's x plus 4 and 5x plus 4. And your answer is not that. It is not complete yet. Why is that? Because I have to take this greatest common factor and put it at the beginning of my answer. I factored it out at the beginning. It is still part of my answer. I can't throw it away and be finished with it. It is still included in my answer. It goes at the very front. Now, my final step is to verify that each of my terms are in its simplest forms. I see that there's no greatest common factor. There's nothing else that I can do, so I am finished. Okay? This next one here. We are going to write the problem down, and first thing, check for our greatest common factor. What is our greatest common factor among these two terms? I see that I have, what here is the biggest? A 2, I believe so. A 2. What about the x's? How many x's can I factor out? X squared. I can also factor out a y squared. Let's see what we're left with after we take out that greatest common factor. I'd be left with 4x to the 4th, no y's, minus 9, and that's it. Now I look at what I'm left with here, and I think, is it a difference of squares or a perfect square trinomial? Well, 4x to the 4th is definitely a perfect square. 9's a perfect square, so that is what we call a difference of squares. We know that from our special products. What does that factor into? 2x squared minus 3 times 2x squared plus 3. Okay? I can't forget about my greatest common factor. I got to carry that down into my answer. Now I want to look at each of what I'm left with here and determine, can those be factored anymore? Are they in simplest form? 2x squared minus 3, that is not a sum of, a difference of squares or a perfect square trinomial. 2x squared plus 3 is not either of those as well. So those cannot be factored anymore. Therefore, my answer is this long thing here in simplest form. All right, here is Coach Wallace to help you with these two examples.
Okay, so looking at my problem, I need to decide, is there a greatest common factor? And I noticed that 9x squared, 3x, and negative 2 have no greatest common factor, so there's not a greatest common factor that I can factor out. The next thing I need to think of, is this a difference of squares? No. Is this a perfect square trinomial? No, because 2 is not a perfect square, so the next thing I can do is I can do my t and my x. I'm not crazy, Ms. Sokolowski. This is just a normal so I can do my t and my x, and you guys can solve that because you've done it 1,000 times. So that one's pretty simple. Now coming over here to 2p to the 5th plus 10p to the 4th minus 12p cubed, you should automatically start to notice that, hey, this has a greatest common factor of 2 for sure, because everybody's a multiple of 2, and it also has a greatest common factor of, I'm looking at my p's, and I think I can take p cubed out because everybody's got at least p cubed. So I'm going to go ahead and I'm going to rewrite this. This becomes p squared plus 5p minus 6. And now I need to think, okay, well, what about my p squared plus 5p minus 6? Well, I'm looking at it, and I'm thinking that this is probably going to be able to be factored. So I need to think about my little x over here and my little t. So this becomes, we've got negative 6 in the top and 5 in the bottom. What can multiply to give me negative 6, but add up to give me 5? 6 and negative 1. Good job, Ms. Sokolowski. All right, so I have my common factor, 2p cubed, and now I'm going to have my two binomials of p plus 6, and p minus 1. And I'm looking at p plus 6 and p minus 1, and those are as low as they go. So this whole baby is my answer. Last one here. We got x to the 4th minus x squared. I'm looking at this and I need to think, well, could this be a difference of squares? What is the square root of x to the 4th? That's x squared. What is the square root of x squared? That's x. Oh, first things first, I should probably factor out a greatest common factor. Oh, it is. So I'm going to factor out my greatest common factor of x squared, and that's going to leave me with x squared minus 1, which I noticed this is a difference of squares. So this is x squared times x plus 1 times x minus 1, and that is as low as it goes. So that is my answer, which I eventually would have gotten to regardless.